Okay, so now we've got episode 2 of or episode 3, rule 2 of building a regression model that we can trust the outputs of because it meets all of our requirements. Today's test, building on yesterday's linearity test, is independence. So we need to make sure that each of the errors aren't related to the previous error. That's known as autocorrelation. This is bad, and it's very common in the stock market when you are using price data, like raw numerical values. For example, if you're regressing on Tesla's share prices numerically, like $325, and you're using a regression model to predict tomorrow's price as, for example, you're predicting tomorrow's price to be $333. Well, if it ends up being $243 tomorrow because Elon Musk decides to say something crazy, like he always does. I can't think of a great example. So Tesla stock just halves tomorrow. And then the price following that will also be like $235, but your predictions will keep being around $335, $336. You'll never be able to, like, those errors will be correlated with each other because they are happening next to each other. That's not good. Share prices generally follow each other for a couple days without like drastically shifting one after another after another. And if there's a correlation between errors, that creates a bad regression test. Again, I'm doing that thing where I just say a lot of words, and it might make more sense when we actually build a test that verifies whether or not we can run this. So let's make another file called regindependence.ipynb for a Jupyter notebook. Load in our standard packages and copy in all of the functions from our last file, reglinearity. We're not going to be using the test linearity test function. We're just going to be getting everything up until that point so we can make a separate file. And then our main function is going to include everything except for, again, that last function. Control Z, Control C, Control V, get rid of this. And then when we run the data frame, or when we get the data frame by running everything and selecting our environment, we should see everything up until this coefficient and intercept. Now, the official name for this test is the Durbin-Watson test, and we can go into the math of that, but I actually don't think that's useful for explaining it. I think if you want to learn the Durbin-Watson test on your own, that is something some people could take initiative to do if they're actually interested in the statistics behind everything we're learning in this process so far. My goal is to give a visual representation for each of these tests. So we can just run the code, see the plots, and assess whether or not there's an issue before moving on. I don't want to teach you the ins and outs of statistics class. I know that sounds a little bit counterintuitive, but I think it would be more fun for me and you just to have a plot designated for each of these tests as opposed to a numerical value. Going into detail about the Durbin-Watson test, I think if I remember correctly, if you have a value around 2, that means there is no autocorrelation. If it's above 2, there might be. If it's less than 2, there might be negative autocorrelation. It's hard for me to explain. I'm actually a bit foggy on it. But I do remember lag plots, and those are easy for me to understand and therefore easy to teach. So we are going to make, much like our linearity plot, a lag plot between residuals. So we're going to test whether or not there's a correlation between one residual and the following. And what we want to see, again, is a random scatter. If there's a clear shape between one residual and the residual following, and however many intervals we choose to lag that relationship between, then there's a problem, and we need to assess that as well. I don't expect there to be a super strong problem because we are, again, assessing percent changes, and there's generally not a strong correlation between percent changes. So we're just going to take another function from pandas, which is the lag plot function. pandas.plotting has a couple really good imports. So import pandas.plotting as pd plt, I guess. Is that a good thing? Actually, we can just do this from pandas.plotting import lag plot. That should be good. So there's a bunch of different functions you can get from pandas.plotting. Today we're just using lag plot, and that just takes a scatter plot between one series and a lagged version of that same series. So we can define test independence, data frame, and we need to plot the residuals, which we might not even have. Do we have those? Data frame. From linearity, I think we might have. Yeah, we made a residuals column in the linearity test, so we're going to actually keep those. Now that I'm thinking about it, I might just don't save this file at all. We're actually just going to build upon reg linearity, and instead of having a reg independence file, making a new file for each test, we're just going to call this regression validation.ipymb. And all 4 of our tests are going to be in this file. So we can just keep building on it in each episode. So now we're going to define test independence of the data frame. And we need to create that same lag plot. So we need to import that function here. So from pandas plotting, import lag plot, run this, select the environment, combined. Oh, this is just everything. I made this yesterday. Okay, so when we're testing independence, the first thing I want to do is create a scatter plot to show you what the hell we're even dealing with in the first place. So we just go plt equal, no, lag plot. We'll do LP equals the lag plot that we imported, data frame residuals. Yep. And we want to drop the NA values, drop NA, so we don't get any issues there. And then plt.plot LP, plt.title. Lag plot of residuals. It's a good name. And then return. We don't need to return anything. We can just make sure the function ends. Return. Add this here. Data. Actually, just test independence. Data frame. I don't think this should give me an error. If I just change it here, okay, that's better. So lag plot is just going to create that whole plt dot notation. We're just going to keep it as a super simple function for now. And a lag plot, ooh. And for some reason I don't see. There we go. Okay. So that's because I forgot to add plt.figure. Now there's no strong line in the middle there, and this is ineffectively random scatter. There's no shape here. There's no obvious diagonal in either direction. There's no curved logarithmic suggestion of these two indexes. So y at a given time and y at a given time plus 1. Y represents the residuals, and these are the residuals at time plus 1. Perfect. So there's no obvious relationship here. There's a little bit of a funnel from yesterday's test, and we're going to have to probably cut off the first 10 to 20 years of our data just to make a more random data plot. Keep that from making this funneling shape. The relationship between the relative strength index and the target as of right now looks to be pretty random, but again, there's a little bit of a shape to our plot, which suggests we're doing a bit of a bad analysis. So we're right now halfway there to creating an effective regression analysis where we can see a bunch of random plots. What we want to see is 4. And then we can make our assumptions more valid. Right now we have these with a correlation coefficient and an R-squared, but we can't really use them without making sure we haven't passed our 4 regression tests first. And that is episode 2. We now have a lag plot of residuals, which is effectively random, which is exactly what you want to see, to make sure that we can keep moving on to the next test, which is homoscedasticity. That is a fun word to say, and we will be doing a fun lesson on that next episode. So thank you guys for following along. You are one step closer to creating a much more advanced trading strategy or regression analysis on anything that interests you going forward. Thanks for sticking around. Make sure to comment, subscribe, and all of that. And until next time, stay sharp.